Hello friends and welcome to another lecture on chemical thermodynamics. Well, for others who have come in to study vapor pressure, don't leave. This is not chemical engineering thermodynamics. This is a lecture on chemical thermodynamics. And if you want to understand the concept of vapor pressure, stick around. Don't leave. The reason is you're going to learn a lot more and a lot better than what you have already learned. Well, why such a basic lecture on vapor pressure? The reason is it's a concept which is not well understood by people who studied in 11th and 12th and who of course finally come to the engineering. After they pass the engineering course, a concept which is very poorly understood. Simple. I am Professor Arvind Prasad and today we are going to study about vapor pressure. So for this we need to understand what is pressure first. Later on we can come to vapor pressure. So let's go ahead. Now whenever we take a vessel, okay, so let's take any vessel and let's say we put gas in it and we measure the pressure, that is the force per unit area which is exerted by the gas on the walls. Okay, so we record the pressure of the gas. Understood? Well, I have not also explained it well and you are also not going to understand it. So let's try and understand how do we practically measure pressure. Most of the problem starts with understanding vapor pressure is the problem of understanding the idea of pressure itself. So let's understand how do we practically measure pressures first. So the practical way of measuring pressure is, of course, there is YouTube manometer, but industrially pressure is measured using a gauge. Now this is a pressure gauge. Okay. Now have a look at this pressure gauge. It has a neat little face on it and it has markings on it. It's circular. This part is known as the stem. Now this stem gets attached to the vessel or to the pipe on which you want to measure the pressure, right? And this is the indicator. Now this indicator moves and shows you the pressure. Now that has really not taught you how do we measure pressure and what it is. So let's get back to the inner workings of this pressure gauge. So this is how it works. This is a hollow metal tube. Hollow metal tube. Okay. Now this hollow metal tube, in this hollow metal tube, if any fluid enters in and if it's under pressure, and anytime if it enters in this hollow metal tube, okay, and it is under pressure, what is going to happen is it's going to apply force on the walls of this hollow metal tube, right? Now what is going to happen is, because it is going to apply pressure, that is force per unit area, or force you can say, on the walls of the metal tube is going to distort. Now because of the distortion, it's going to lift up, it's going to straighten up. Now because it has a tendency to straighten up, when a fluid under pressure rushes into it, this link is going to get pulled, and when this link is pulled, this moves the sector gear which moves the pointer. So it's but natural that such kind of gauges are at rest when you have atmospheric air going into it. Okay, or you need to understand one thing, they're just simply at their original position when there's atmospheric pressure into it. Yeah, so let's come to the idea of atmospheric pressure. So we need to understand that what is atmospheric. We all live under pressure, not the pressure of studies or making money, but we all physically live under a pressure of 1 atmosphere. Why? Because the air around us exerts a pressure on us. We simply don't realize it, but it is there. The first idea that air was exerting a pressure was, it was very simple. You took liquid and then you took a tube, filled with the same liquid. You took a tube filled with the same liquid to the top, and then you overturned the tube and put it into the liquid. Now what would happen is the liquid would fall, and then it would come at an equilibrium position, not fall completely. Why? Because the atmosphere is appearing or applying a pressure on this liquid surface, because of which the liquid rises. Remember one thing, when the liquid leaves this and falls into this pool of liquid, a vacuum is going to get created here. So there's no effectively any pressure in this. So the liquid rise in this is only because of the outside pressure or the atmospheric pressure or the pressure applied by air. So this was the first idea of demonstrating that we live under a pressure. The pressure exerted by air around us. So this pressure, anytime, everywhere, if you measure at the sea level, the height of liquid would be same. And if you looked at the height of water, this would be 10 meters. Okay, so this 10 meter of water height was given a name of 1 atmosphere. This was given a unit of 1 atmosphere. Right? So this is the way our atmosphere first in the baby steps got defined of understanding atmospheric pressure. And then afterwards, back to the Bodengage. So if we go back to the Bodengage and try and understand it, okay, let me remove this off. Yes, so back to the Bodengage. This is known as a Bodengage. So it's but natural that these are designed in such a way that whenever they are open to atmosphere, they show a reading of 0. 0 bar. That's 1 atmosphere. But remember one thing, 0 bar, it's calibrated to 0 at 1 atmosphere. Okay, it's calibrated. The pointer is just set to 0. It's not 0 exactly. Now, whenever the fluid entering it has a pressure greater than 1 atmosphere, it's going to rise. Understand that once again. Whenever a fluid coming in this gauge has a pressure greater than 1 atmosphere, this gauge is going to move. And it's going to move because the fluid is going to enter in this Bodengage or Boden metal tube as you call it. Now this is going to distort and this is going to give you a reading. So far so good. Understood. How does it work? Let's get further. So this is going to be the representation of a pressure gauge. This is the usual representation we have of a pressure gauge. It's here. This is the usual representation of pressure gauge that you have. Now, if you take any vessel which is open, the pressure in it is going to be 1 atmosphere. And if it is open to the atmosphere, it's going to be 1 atmosphere. Now, if you close it, well, if it is, I am filling gas in this, I can fill more and more and more gas in it. The more gas I push into it, the pressure of the gas is going to rise. Because the force exerted by gas on the walls of this vessel is going to rise. So how do we measure the force? It's very simple here. If we have to measure this force, a good way industrially is, of course, take this Bodengage. Okay. Take it and place it over the vessel that you have. Yes. And after that, just close it. And there you are measuring the pressure of this gas. Right? Now, what about liquids? If I have an open tank, this surface of liquid is experiencing a pressure of 1 atmosphere. But if I put a gauge at the bottom, now let me take this gauge and I will connect it through some means at the bottom of this tank using a small pipe, I would get a pressure greater than 1 atmosphere. The pressure would be higher than 0. Now why? That is because the liquid has a density, that is weight per unit volume, or mass per unit volume. Okay. And then because of that, the pressure at the bottom is going to be 1 atmosphere plus the height of the liquid h, okay, rho into g. So it's weight per unit volume. Okay. So weight per unit volume or mass per unit volume is the density multiplied by gravity. That's going to be the weight per unit volume, and multiplied by h, you are going to have the pressure exerted by the liquid height. And over and above, you have 1 atmosphere. So it's going to be that much. But then for all practical purposes, this gauge is only going to measure h rho g because it is set to 0 at 1 atmosphere. Right? Now, I have discussed the concept of pressure and how we measure it. Right? Now, pressure, once again, before we go ahead, is force per unit area exerted by the fluid in a vessel. Pressure, nothing, is but force per unit area exerted by any fluid which is in a vessel. Now, getting back to our problem, what is vapor pressure? Now, let's open this up, vessel, and for a moment, let's shift the pressure gauge and take it somewhere else. Okay, so let's shift it up. Now, if we put liquid into this tank, one thing is very sure. You may not observe it. Many people don't experience it and that is why there is a huge debate sometimes. Many people have. The liquid is constantly evaporating. Well, in other English language, in a better English language and a scientific language, we can also say that the liquid is constantly vaporizing. Evaporating, constant vaporization, one and the same. They have one and the same implications or meanings. Now, the thing here is that whenever the molecules of this liquid leave the surface of the liquid and become vapor, it requires energy to do so. Now, this energy is given by the surroundings itself. We need to understand this very clearly. Vaporization does require energy. Now, this energy is taken by the surroundings. Now, what energy, you would question? The energy would be obviously in form of heat. It has to take heat from the surroundings in order to vaporize. If the heat given is insufficient, the rate of vaporization is insufficient. But in any case, there's vaporization going on. Okay, so now let's further extend this and understand the vapor pressure. So there's vaporization going on. Now we'll do a simple trick. We'll put the liquid in this and we'll keep it open to the atmosphere. Then suddenly, that's all of a sudden, suddenly means all of a sudden, we cover it up. Cover it up. Now the vapors can no longer escape to the atmosphere, but they can only escape to the limited space that it has between the top of the vessel and the surface of the liquid, where it can accommodate itself. Now what is going to happen is the molecules are going to vaporize into this empty space. Okay. And let's do something more interesting here. So what we do is we make a small slit here and we take this pressure gauge and we put it up here once again to see what really happens. Okay. So take it here, connect this. Still, the vapors can't escape to the atmosphere. They can only at the most go to the pressure gauge. Initially, when you put it, the pressure gauge is going to read 0. So let's take the time and let's take the reading of the pressure gauge. It's going to read 0. Now it will rise up with respect to time and it will flatten and become a constantly extending but a straight line, and this would be a constant value of pressure that you would get. Why would that happen? That would happen because as the vapor molecules crowd in the empty space by rising out from the fluid, they are going to also go back into the liquid. Why? Because they have no more space. So crowding is going to occur, and the crowding at one point of time is going to become so much that it's going to enter in back also. Well, do they not enter in before the crowding occurs? They do. But the rate at which they enter into the liquid and the rate at which they are leaving the liquid is unequal. The rate at which they are leaving the liquid is higher. But as the crowding occurs, the rate at which they leave the liquid and come back to the liquid is constant. This condition is known as saturation. Saturation means what? You can take it no more. You can take it no more. So the vapor space which is above the liquid surface can take it no more. No more vapors, please. So that's known as the saturation condition. And this pressure that we read at that point of time is known as the saturated vapor pressure. Now, it's obvious we are reading the pressures of the vapor. We are reading the pressure of the vapors. The vapors are exerting the pressure. Initially, it read 0 because there was only atmosphere. We covered it up. Suddenly, the vapor, the space above the liquid got congested of the air that was initially there, and it got congested because of the more and more vapor molecules that came in. But then as it got saturated off, there was an equilibrium. Equilibrium means number of molecules leaving the liquid surface and coming back to the liquid surface, same. The rate is same. So we come to an equilibrium, and therefore at the equilibrium the pressure we read is the saturated vapor pressure, and that is commonly known as vapor pressure. But please understand that whenever anybody is trying to talk about vapor pressure or giving you a value of the vapor pressure, he's in all probability giving you the value of the saturated vapor pressure, because you have data of the saturated vapor pressure itself, available. So let's have a look now. How does the saturated vapor pressure graph really look like? You have the saturated vapor pressure here, and you have the temperature here. Now this graph is going to look something like this. Okay, so the obvious thing here is that as the temperature goes up, the vapor pressure goes up, and as the temperature reduces, the vapor pressure reduces. But watch out, it's not a straight line. So the rate of increase of vapor pressure at different temperatures is different. The rate of increase of vapor pressure at lower temperatures is different from rate of increase of vapor pressure at higher temperatures. One cannot, in all folly, take the same rate and make a conclusion. And how are you helped with that? You are helped by the famous Antoine's equation. So the Antoine's equation is ln p sat is equal to A minus B upon T plus C, where T is the temperature. Okay, A, B, C, they are constants. So you plug in the pressure here, you plug in the temperature here, you get the vapor pressure. You plug in the temperature here, you get the vapor pressure. And it's very simple. This equation also is not a linear equation. Okay, therefore, you have Antoine's constant available for common fluids, common liquids. It's available. This voluminous amount of data is all around available to you in chemistry books, chemical engineering, thermodynamics handbooks on Antoine's constant of various common fluids that we use. It's available. One source of data is also MSDS, that is Material Safety Data Sheet. It does give you Antoine's constant. Sometimes they do mention it. They at least mention what is the vapor pressure at normal boiling point and atmospheric temperatures, that is standard, that is 25 degrees Celsius. Okay, so before we leave from here, we need to understand here that vapor pressure is higher at higher temperatures. Now, what's the meaning of this? The meaning of this is whenever you're storing liquid in any enclosed vessel, which is a tank. In most of the chemical engineering plants, you will see a tank. Whenever you're storing liquid in a tank, you cannot design it by simply believing that the pressure in this tank is going to remain 1 atmosphere. Please do not be under this folly. The pressure eventually is going to be higher because vapor is going to get accumulated in the empty space and apply vapor pressure. So the pressure over and above the atmosphere is the vapor pressure. Simple. That's simple. That's very basic. Okay, what this gauge will measure over and above the atmospheric pressure is always going to be the vapor pressure. To start with, it was measuring 0, which was the pressure of atmosphere, because to start with, we put liquid and the tank was open. Then we suddenly covered it up. Now, whatever pressure that it gains, whatever pressure reading that it gains is the vapor pressure, because that is pressure exerted by the vapors, or the saturated vapor pressure. If we wait long enough, we get the saturated vapor pressure at the temperature of the liquid. And the saturated vapor pressure is proportional to the temperature, but it's not linear. Right? So this was the idea of pressure. By gradually introducing the idea of pressure, we came to the idea of what is vapor pressure. And we also saw the practical implications of understanding the phenomenon of vapor pressure, or understanding how vapor pressure plays an important role in design of vessels and what vapor pressure shows. Okay, if you're not interested in a chemical engineering example, a more a day-to-day example would be liquids that have higher saturated vapor pressure at a given temperature are liquids that would evaporate easily. Liquids that have very low saturated vapor pressure at a given temperature are liquids that would not evaporate easily. They would evaporate very, very slowly. Okay. So liquids which have high vapor pressure evaporate fast. Liquids that have low vapor pressure evaporate very slow. If I take a mixture in which I have one liquid which has a very high vapor pressure and second liquid which has a very low vapor pressure, mix them, the component which has a very high vapor pressure would evaporate off quickly. No doubt the component which has low vapor pressure would also evaporate, but eventually what you would find is the concentration would change, and after a long period of time you would only have liquid which has low vapor pressure in higher concentration, and liquid which has high vapor pressure simply disappears off. It leaves the vessel, it leaves the mixture, and you find very less concentration of that at a later time. Now that would also depend on what the vapor pressures are. The quantity, the concentration depends on what the vapor pressure is and under what pressure it is evaporating. Right. Therefore, this is what we understood about vapor pressures. And if you have any more questions, any more doubts on vapor pressure, do let me know by writing comments. I would clarify them. Be open. Tell me what you want to know. Write in your comment. I'll explain it. Right? I'm here for you. This is Professor Arvind Prasad signing out. Do like and subscribe my channel if you like it. And if you have already subscribed, extend my playlist or send my playlist to people who haven't subscribed and request them to subscribe it off if they like it. Well, I have 2 decades of experience teaching chemical engineering and chemical engineering thermodynamics. I was also an ex-scientist of Bhabha Atomic Research Center. I have a lot to share with you. Keep watching my videos. Bye.